You want to build a planet. Not terraform one, not colonize one. Actually construct a sphere of rock and metal and maybe some water that orbits a star and could, if you're lucky, host life. You'll need about 6 septillion kilograms of matter, a few billion years of patience, and a surprisingly simple set of instructions that the universe has been following since shortly after the Big Bang. The process is messy, violent, and happens to be running right now in stellar nurseries across the galaxy. Every planet in our solar system followed these same brutal steps. And somewhere out there, new worlds are condensing from chaos as you read this. Let's walk through how you do it yourself. First, you need a nebula. Picture a cloud of gas and dust stretching trillions of kilometers across space, left behind by dead stars that exploded and seeded the cosmos with heavy elements. This isn't empty space. It's a diffuse fog of hydrogen, helium, and trace amounts of everything else: carbon, iron, silicon, oxygen. The density is absurdly low, maybe a few thousand atoms per cubic centimeter, which is still 1,000,000 times thinner than the best vacuum we can create on Earth. But you have an enormous amount of it. Inside this cloud, tiny variations in density become important. Maybe a shock wave from a nearby supernova passes through, or the cloud just collapses under its own gravity. Either way, certain regions start to pull in more material. Gravity is patient and relentless. Where there's slightly more mass accumulates. The cloud begins to fragment into clumps, each destined to become a star system. You're going to focus on one clump, one future solar system, and claim a small percentage of its material for your planet. Here's the catch. You can't build planets without a star. The collapsing clump of gas spirals inward, spinning faster as it shrinks, like a figure skater pulling in their arms. Most of the mass, about 99% of it, falls toward the center, heating up from compression until hydrogen atoms start slamming together hard enough to fuse into helium. Congratulations! You've ignited nuclear fusion. You now have a protostar, a young star that's still gathering mass and glowing with the heat of its formation. The remaining material settles into a disk around this newborn star, a flat, spinning pancake of gas and dust called a protoplanetary disk. This disk is where your planet will form, and it's already sorting itself by temperature. Close to the star, it's hot enough to vaporize rock. Further out, ices can survive. This temperature gradient determines what kind of planet you can build where. Rocky planets form near the star. Gas giants form in the cold outer regions. You're stuck with these zones. Inside the disk, dust particles are colliding constantly. Most bounce off each other, but some stick through electrostatic forces and van der Waals interactions. The same forces that let geckos climb walls. A fleck of dust hits another fleck, and they cling together. Do this trillions of times, and you get pebbles, then rocks, then boulders. This early stage is slow and fragile. Collisions can shatter your growing rocks as easily as build them. But once a chunk reaches about a kilometer across, its own gravity starts helping. Now, it's not just sticky forces. The rock is actively pulling in nearby material. These kilometer-sized bodies are called planetesimals, and they're the building blocks of planets. The disk is now filled with billions of these objects, all orbiting the star, all occasionally smashing into each other. Some collisions are gentle mergers. Others are catastrophic, spraying debris back into space. The survivors grow. After a few 100,000 years, you have objects the size of mountains and moons, sweeping up everything in their orbital paths. Now things get destructive. The largest planetesimals have become planetary embryos, objects the size of Mercury or Mars, with enough gravity to dominate their orbital zones. But the disk is crowded and chaotic. Embryos collide with each other in impacts that release more energy than all nuclear weapons ever built, detonated simultaneously. Each collision melts both objects into expanding clouds of vaporized rock that recondense into a single larger body. Your growing planet is molten, glowing orange from the heat of constant bombardment. Heavier elements like iron sink toward the center, while lighter silicates float to form a mantle. This is differentiation, and it's crucial. A planet needs a dense core and a rocky mantle to have the right structure. The impacts continue for tens of millions of years. Your planet might get hit by another Mars-sized object in a glancing blow that tears away a chunk of mantle and sends it into orbit, where it coalesces into a moon. This isn't speculation. It's probably how Earth got our moon. Eventually, your planet has swept up most of the material in its orbit. The bombardment slows. The surface begins to cool and solidify into a crust. If you want your planet to be interesting, it needs an atmosphere and possibly water. These arrive through two paths. First, your planet formed from material that contained volatile compounds, water ice, carbon dioxide, ammonia, trapped in the rocks and released during impacts and volcanic eruptions. This outgassing creates a thick early atmosphere, though it probably doesn't resemble anything you'd want to breathe. Second, the outer solar system is full of comets and asteroids loaded with ice. During a period called the Late Heavy Bombardment, gravitational interactions send swarms of these icy bodies careening into the inner solar system. They pummel your planet, delivering oceans worth of water in violent impacts. This sounds terrible for any potential life, but it's also delivering the raw materials life needs. Your planet now has liquid water pooling in basins, an atmosphere with greenhouse gases keeping the surface warm enough to stay liquid, and a protective magnetic field generated by its spinning iron core deflecting radiation from the star. The surface is still hostile. Constant volcanic eruptions. An atmosphere of carbon dioxide and nitrogen. Oceans that are probably acidic. But it's stable enough for chemistry to get interesting. You've built your planet. Total construction time, about 100 million years. From the first dust collisions to a stable world with continents and oceans. But you're not done. Planets continue evolving for billions of years. Plate tectonics might start, recycling the crust and regulating atmospheric carbon dioxide. An oxygen-producing organism might evolve and terraform the atmosphere. Moons stabilize the axial tilt, creating stable seasons. Or none of this happens, and your planet becomes a frozen ice ball or a scorched desert. The difference between Earth and Venus, one a paradise, one a hellscape, comes down to small variations in distance from the Sun, rotation rate, and initial water content. You don't get to control these precisely. Building a planet is like rolling weighted dice. You can influence the odds, but not guarantee the outcome. What you've really built is a stage. Whether anything interesting happens on that stage over the next 4 billion years depends on countless variables you set in motion but can't control. And that's the remarkable thing. This violent, chaotic, seemingly random process has created trillions of planets across the galaxy. Some are barren, some are bizarre, and some, against enormous odds, might be looking back at us right now, wondering if they're alone.